Within a night sky that seems calm and still, the universe is quietly carrying out immense motions of its own. Not in flashes of blinding explosions, not in moments of violent endings, but along delicate boundaries, where a star seems to ask how long it can remain standing against the steady pull of its own gravity. What decides when a star continues to endure, when it collapses inward, and when it crosses into a state entirely different from anything our everyday intuition expects? Are the objects we call black holes always the final destination? Or does the universe preserve quieter, more subtle possibilities just beyond that edge? In this journey, we will not rush toward answers. Instead, we listen to the way the universe balances inward pull and outward response, certainty and the unknown. If this sense of quiet curiosity stays with you, feel free to leave a comment, offer a gentle like, share, or subscribe to remain part of the exploration. For now, allow yourself to relax and prepare to move into the deeper layers of the story. Waiting ahead, far above us, the sun holds its place in the sky as if it has always been there and will always remain. When we look toward it, even in imagination, we are meeting a vast sphere of hot, ionized gas without a solid surface, held together by its own gravity. Every bit of matter inside that glowing sphere feels a continuous inward pull, drawing it toward the center. At the same time, light and particles flowing outward from the core press gently against that pull, so that the star neither flies apart nor collapses inward. If we picture ourselves drifting toward the outer layers of the sun, we can let the details of equations fall away and simply notice this balance. Gravity is always trying to draw material inward, layer by layer, while radiation from nuclear reactions in the core pushes outward through the gas. The outer regions we call the surface are not a hard boundary at all, just the place where the gas becomes thin enough for light to escape freely. For our purposes, it is enough to remember that a star is a conversation between inward pull and outward push, continuing quietly over immense spans of time. Inside, hydrogen nuclei move and collide at such high temperatures that they combine to form helium. This process of fusion slowly changes the composition of the core while releasing energy. That energy flows outward as light and particles and, in doing so, provides the outward pressure that holds gravity in check. As long as the fuel in the core continues to support fusion at the right rate, the star rests in a kind of long-term balance, shining steadily and holding its shape while planets, dust, and smaller bodies travel around it. Over time, however, the story of a star like the Sun does not stay the same. As hydrogen is gradually transformed into helium, the core becomes denser and hotter. Fusion begins to shift to new layers and new reactions. The star swells outward into a red giant, its outer layers stretching far beyond their original reach. The familiar, compact sun of our daylight imagination becomes a much larger, cooler, and more extended object. While deep inside, the core contracts and changes character. The same theme remains: gravity pulling inward, some form of pressure pushing outward. The details of what provides that pressure begin to change. When the outer layers are finally lost to space, what is left behind for a star like the Sun is a white dwarf, a compact Earth-sized remnant that no longer shines by ongoing fusion in its core. Instead, it glows with leftover heat, slowly fading over immense durations. The matter inside a white dwarf is packed so tightly that ordinary explanations about gas pressure no longer apply. Electrons, which normally move freely around atomic nuclei, are pressed together until the quantum rules that describe them resist further compression. That resistance is called electron degeneracy pressure, and it quietly takes over the role of supporting the star against gravity when nuclear reactions have stopped. From a distance, a white dwarf looks small and dense, the final stable stage for many stars. Yet not every star can end its life this way. If the remaining core, after the outer layers are lost, is too massive, roughly around 1.5 times the mass of the Sun, electron degeneracy pressure can no longer provide enough support. There is a threshold where this quantum pressure reaches its limit. Below that threshold, a white dwarf can persist for longer than any human timescale. Above it, further collapse becomes unavoidable, and the star must look for a different form of support. For more massive remnants, the collapse continues until protons and electrons are squeezed together into neutrons. The result is a neutron star, a sphere only about as wide as a large city, yet containing more mass than the Sunday. Inside, matter is compressed to densities far beyond anything we encounter in daily life. The neutrons crowd together in ways that again call on quantum rules, producing neutron degeneracy pressure, which holds gravity at bay. Here, the theme of balance appears once more, but now in an even more extreme form. Gravity trying to continue its inward pull, and a new kind of pressure emerging from the behavior of particles at the smallest scales. Even neutron stars, however, cannot support any amount of mass. If the remnant becomes heavier than a certain limit, a bit more than twice the mass of the Sun according to many models, neutron degeneracy pressure is no longer sufficient. At that point, our familiar catalogue of pressure sources, thermal motion, fusion, electron degeneracy, neutron degeneracy, has been exhausted. There is no known form of ordinary matter that can provide the necessary counterforce. These limits mark a boundary in our understanding. Below them, white dwarfs and neutron stars can stand against gravity. Above them, we expect something even more compact to emerge. When a collapsing remnant crosses that boundary, gravity is no longer matched by any internal pressure arising from normal matter. The object continues to shrink until, for an outside observer, its size falls within a particular radius set by its mass. This radius is often called the Schwarzschild radius, a distance from the center at which the escape speed equals the speed of light. Once the collapsing matter passes inside this radius, light itself can no longer travel outward to distant observers. What remains, from our point of view, is a black hole candidate. A region of space-time whose presence can be inferred from its effects on surrounding matter and light, but whose interior structure is hidden from direct view. At this stage, the star as an object with a visible surface has disappeared. We no longer speak of a glowing photosphere or a crust. Instead, we speak about an event horizon, a boundary in space-time that separates the region from which light can reach us from the region from which it cannot. The simplicity of a black hole description stands in contrast to the rich internal structures of white dwarfs and neutron stars. Mass, spin, and electric charge become the main quantities we use to describe these compact objects. While the detailed history of the star that formed them fades into the background, seen from far away, many compact objects near this threshold can look very similar. Whether we observe X-rays from gas spiraling inward, or the subtle timing of pulses from surrounding material, our instruments pick up the influence of strong gravity rather than a clear picture of a surface. When gravitational wave observatories listen for the ripples produced by merging compact objects, the signals often tell us about the masses and spins involved, but not always about whether the final object has a hard surface or a horizon. In that sense, some of the companions we call black hole candidates might, in principle, be extremely compact stars that sit just outside the radii we associate with black holes. For now, it is enough to hold on to the pattern that ties all these stages together. Ordinary stars, white dwarfs, neutron stars, and black hole candidates can all be viewed as different answers to the same question. How does the inward pull of gravity find balance, or fail to find it, in different kinds of matter? As we move slowly from the familiar territory of the Sun and its long-lived balance into the more extreme territory of compact objects and thresholds, other possibilities begin to appear at the edges of theory. Somewhere near those thresholds, ideas about more exotic stars and structures start to take shape, waiting quietly at the boundary between what we have confirmed and what we still treat as open exploration. As we follow the path from ordinary stars into more compressed forms, we eventually encounter a quieter kind of boundary, one that does not come from the details of nuclear reactions or quantum particles alone, but from the overall geometry of space-time itself. In this region of thought, gravity is still an inward pull, and pressure is still the balancing response. Yet the shape of the possible star is constrained by a deeper rule. The familiar idea of a star as a sphere of matter held up by its own internal support is still present. But now, a mathematical limit begins to frame how compact such an object can be if its material behaves in ways we would call ordinary. To describe that limit, we imagine a star made of matter with positive energy density and positive pressure, the kind of material we expect for white dwarfs and neutron stars. Around such an object, we can define a characteristic radius associated with its mass, the Schwarzschild radius, a distance from the center where, if the star were somehow compressed inside that sphere, light trying to escape would find the outward path completely cut off. For a true black hole, the object's mass lies within this radius, and an event horizon forms. Buchdahl's result tells us that if the matter remains normal in the sense of positive pressure and energy density, then a stable star cannot be squeezed right down to that boundary. Its radius must stay a little larger, never quite touching the horizon radius that a black hole of the same mass would have. This limit acts like a subtle wall in our description of compact stars. Even if we push the equations as far as they allow under ordinary conditions, the equilibrium configurations stop short of the horizon. A neutron star, for example, can be very compact, but not arbitrarily close to the radius associated with a black hole of equal mass. There is always a small but meaningful gap. In principle, this means that a star supported by ordinary pressure sources and obeying familiar energy conditions cannot perfectly mimic a black hole. At least in theory, its surface sits just outside the location where an event horizon would form. From a geometric point of view, this boundary encourages us to think about extreme stars in two layers. On one side, there are compact objects built from matter whose pressure and energy density both remain positive, limited in how tightly they can be compressed before collapse proceeds toward a black hole. On the other side, there are hypothetical objects that would require us to relax those assumptions, allowing the pressure to take on forms that are less familiar in everyday physics. The Buchdahl limit, therefore, provides motivation for exploring matter models that are not simply denser versions of what we already know, but something structurally different. To move into that territory, theorists turn to the Tolman-Oppenheimer-Volkoff equation, the relativistic description of hydrostatic equilibrium in a spherical star. This equation quietly combines gravity, pressure gradients, and energy density into a single balance, telling us how pressure must change from the center of the star to its outer layers if the object is to remain static. When we restrict ourselves to positive pressure, the solutions behave smoothly. Pressure is highest at the center and decreases outward until it reaches zero at the surface, where the star meets the surrounding vacuum. However, if we allow the pressure at the center to become negative and large in magnitude, the behavior of the solutions changes in a striking way. Instead of a smooth decline from the center to the surface, the equation demands that the pressure dive toward enormous negative values, reverse sign at some inner radius, and then climb back up again, eventually reaching zero at the boundary. This pattern introduces a singular layer inside the star where the description ceases to be well-behaved unless the central pressure is tuned to a very special value. Most choices of negative central pressure lead to internal structures that are considered unphysical because of this divergence. Only a particular case avoids this difficulty. When the pressure is negative and has the same magnitude as the energy density, remaining uniform throughout the interior. In that finely adjusted configuration, the pressure profile becomes smooth again, with no inner singular layer. The star's interior is then filled with a medium whose properties are very different from ordinary matter. Gravity, due to the energy density, pulls inward, while the negative pressure contributes an effect that acts in the opposite direction in the relativistic field equations. The two influences can cancel in such a way that the interior becomes free from net gravitational pull. This is the basic idea behind a gravastar, or gravitational vacuum star. Inside such an object, the energy density is positive, and the pressure is negative with the same magnitude, constant across the whole volume. There are no pressure gradients to push matter one way or another, no inward or outward force acting on a small test particle placed in the interior. Instead, that particle would drift without preference, as if suspended in an idealized vacuum, even though the energy and pressure are not zero. The interior behaves more like a region filled with vacuum energy than a conventional gas or fluid. In cosmology, a similar description appears in models of dark energy, the component that seems to drive the accelerated expansion of the universe on the largest scales. There, too, the combination of positive energy density and negative pressure plays a role, with the ratio between them close to -1. When we recognize that the interior of a gravastar is described in the same way, the object takes on a new character. It becomes a conceptual bridge between stellar physics and cosmic expansion, a kind of star built not from ordinary particles packed ever more tightly, but from something that behaves like vacuum energy confined within a finite region. Gravastars remain theoretical constructions proposed as possible alternatives to black holes rather than confirmed objects. Yet their properties lead to an interesting consequence. As we adjust the parameters of a gravastar solution, the radius of its outer boundary can be brought very close to the Schwarzschild radius for its mass. In that limit, the surface lies only slightly outside the location where an event horizon would appear in a black hole solution. Light and matter near the surface experience enormous gravitational redshift and strong curvature, so that very little radiation escapes to distant observers. From far away, the object looks almost identical to a black hole of the same mass. This near match introduces a quiet ambiguity into our interpretation of certain observations. When telescopes track the motion of stars orbiting a compact central mass, or when instruments like LIGO listen to the gravitational waves produced by merging compact objects, the signals they record are shaped primarily by mass, spin, and the degree of compactness near the would-be horizon. If an object sits just outside that radius, with no true event horizon but with a very small surface emitting almost no light, the observational signatures can resemble those of a black hole candidate quite closely. For this reason, some discussions of extreme compact objects include a reminder that what we label as a black hole in observations might, in principle, be a star-sized configuration that imitates many of the same external effects without actually possessing an event horizon. The simplest and most widely used models still treat these objects as black holes because that description fits the data efficiently and with few assumptions. Yet the existence of gravastar solutions in the theory shows that space-time allows other possibilities, in which negative pressure and vacuum energy take center stage inside a compact object. The presence of these alternatives does not overturn our understanding of stellar remnants, but it does keep a small space open for further exploration. Somewhere between the familiar neutron star and the idealized black hole lies a spectrum of hypothetical structures, each one balancing gravity in its own way. As our instruments continue to refine their view of compact objects and the regions around them, these possibilities remain in the background, part of the quiet landscape of ideas that frame how we think about the extremes of the universe and the delicate boundary between what we can see directly and what we infer from the patterns of light and space-time around us. Far from us, where light curves and time stretches around compact masses, the universe carries out quiet experiments that we mostly witness through their distant traces. When two very dense objects spiral toward each other and merge, they disturb space-time itself, sending out waves that can be recorded by sensitive detectors on Earth. These ripples, measured by observatories such as LIGO, do not show us a photograph of the objects involved. Instead, they offer a pattern, a changing tone in space-time that hints at what those objects might be. In our usual picture, the most extreme of these companions are black holes. The defining feature in that picture is the event horizon, a boundary that marks the point beyond which light and information cannot travel outward to the rest of the universe. For any mass, there is an associated Schwarzschild radius that tells us where that boundary would lie if the object were a simple, non-rotating black hole. If the real object is compressed inside that radius, we say a horizon has formed. If it remains even slightly larger, there is no horizon. And in principle, light or other signals can still escape from its surface, however faint they may be. This distinction between inside the horizon and just outside is clear in theory. Yet in practice, we only see what reaches us from far away. When two compact objects merge, the gravitational waves they produce rise to a maximum as the objects collide, and then settle into a phase called the ringdown, where the final object vibrates in space-time and gradually returns to a quieter state. For a black hole with a true event horizon, the ringdown signal has a characteristic fade, shaped by the way space-time behaves just outside the horizon. If, instead, the final object were a star-like configuration with no horizon, only a surface extremely close to the Schwarzschild radius, the ringdown might not be exactly the same. Some theoretical models suggest that the waves could bounce between the surface and the surrounding curved region, leaving behind small additional structures in the signal, sometimes described as echoes. These would not be dramatic bursts, but faint repetitions that slowly fade. The idea is that the presence or absence of a horizon could, in principle, leave fingerprints in the fine structure of the gravitational wave signal, and that careful listening over long stretches of data might reveal whether a compact object is a traditional black hole or a near black hole star. Alongside gravitational waves, astronomers also study electromagnetic radiation from the regions around compact objects. Gas spiraling inward can heat up and emit X-rays. Disks of material can glow in many wavelengths. Stars orbiting near a massive central object can have their paths traced over years and decades. From these observations, researchers infer the mass of the compact object and estimate how close the visible matter can come before disappearing from view. In a few systems, the inferred radius of the central candidate approaches the Schwarzschild radius to a striking degree, matching it to many decimal places in the models used to fit the data. Even so, an approximation is still an approximation. Observations always come with some level of uncertainty, and the statement that an object's radius is equal to a certain value really means that it lies within a narrow band around that value. Within that band, a true black hole and a gravastar-like configuration could both reside. From a practical point of view, the object behaves as if it has a horizon, because anything close to its surface experiences such strong redshift and time dilation that almost nothing escapes. From a theoretical point of view, however, there remains a small but non-zero window in which a horizonless exotic star could fit the same measurements. In this way, the universe presents us with compact objects whose external behavior so closely matches that of black holes that, for many purposes, we treat them as such. Yet the existence of theoretical alternatives means that our labels carry a quiet caveat. We observe strong gravity and compactness consistent with black holes, while still recognizing that other solutions to the equations of general relativity might occupy almost the same space in our models. The boundary between confirmed black hole and black hole candidate stays slightly open, especially when we look as close as possible to the horizon scale. This openness becomes more visible when we turn to ideas that connect compact objects with the large-scale behavior of the universe. In recent years, some researchers have explored whether black holes might play a direct role in the phenomenon we call dark energy. Dark energy is inferred from the accelerated expansion of the cosmos and is often modeled using vacuum energy with negative pressure. Because the interior of a gravastar resembles such a medium, it is natural to ask whether real astrophysical black hole candidates might conceal vacuum energy like cores rather than classical singularities. A particular study proposed that the masses of certain large black hole candidates tracked across cosmic time appeared to grow in a way that mirrored how dark energy contributes to the expansion of the universe. By comparing these trends, the authors suggested that the objects might not only sit within a universe affected by dark energy, but might themselves be composed of something similar to it, acting as localized pockets of vacuum-like energy. In this view, the line between black holes and gravastar-like structures becomes blurred, and compact objects join the broader conversation about the origin of cosmic acceleration. The response from the wider community illustrates how scientific ideas move through stages of exploration and testing. Observational astronomers examined the data used in the study and questioned how the sample was selected, how uncertainties were handled, and how alternative explanations might account for the same trends. Theorists focused on the way cosmic expansion influences local systems, pointing out that the link between large-scale dark energy and the detailed mass growth of individual compact objects requires careful treatment. They highlighted the difference between the universe's overall expansion and the dynamics within galaxies, where gravity from stars, gas, and dark matter dominates the behavior of black holes over long periods. None of these reactions erase the possibility that compact objects and dark energy might be related in deeper ways. They simply insist that any such connection must pass through several layers of scrutiny. Data must be re-examined with different methods. Theoretical assumptions must be checked against existing frameworks. Alternative explanations must be considered alongside the new proposal. In this process, skepticism is not hostility but a form of care, making sure that the patterns we see in observations truly require new interpretations rather than arising from familiar effects or incomplete modeling. From the perspective of our quiet journey through stellar extremes, what remains most striking is not the headline of any single study, but the way the picture of compact objects stays slightly incomplete. Black hole candidates can be measured with high precision. Yet the last fraction of distance between a physical surface and a horizon remains a subtle region where theory allows more than one structure. Gravastars and other exotic stars occupy that region in our equations, while gravitational wave observations and high-resolution images continue to narrow the possibilities without fully closing them. In this space between confirmation and speculation, the universe leaves room for objects that almost become black holes, and for stars made of something that acts more like vacuum than like ordinary matter. Our instruments keep listening for ripples in space-time and tracing orbits around compact centers, while our models accommodate both familiar horizons and more unusual interiors. For now, the cosmos offers us a landscape in which several descriptions sit side by side, and we move onward with that coexistence in mind, carrying forward the sense that at the very edges of stellar structure, clarity and uncertainty travel together. On the sky we know with the unaided eye, Betelgeuse appears as a bright reddish point near the familiar pattern of Orion. It looks large and close in our imagination, yet in geometric terms it is a distant object, hundreds of light years away, subtending an angle so small that even powerful telescopes see it not as a clear disk, but as something closer to a blurred mark. By comparison, the Moon spans about half a degree, and a planet like Jupiter covers a much smaller but still noticeable patch of sky. Betelgeuse, though truly vast in physical size, occupies a patch of angle that is thousands of times smaller than the Moon's disk. For nearby objects, such as the Sun, we can study surface structures directly, tracing dark spots and bright regions as they drift across the visible face and learning about rotation from the time they take to move. That kind of direct tracking is not available for a star like Betelgeuse. Its apparent size is simply too small for us to watch individual features travel across it in a straightforward way. Instead, our information comes from something more abstract: the way its light is distributed across different wavelengths, and how that distribution shifts in subtle patterns when the star moves. This is where the idea of rotation becomes tied to spectra rather than images. If a star spins, one side of its surface moves slightly toward us, while the opposite side moves slightly away. The light from the approaching side is shifted very slightly toward shorter wavelengths, and the light from the receding side is shifted toward longer wavelengths. The effect is modest, but with instruments that can divide the starlight into extremely fine wavelength bins, these small displacements can be recorded and interpreted. The underlying phenomenon is a version of the Doppler effect. Many of us know it from sound. A passing siren has a higher pitch as it approaches and a lower pitch as it recedes. Light behaves in a similar way. When the source is moving toward us, the waves are compressed. When it is moving away, the waves are stretched. For a rotating star, half the visible surface contributes slightly shifted light in one direction and the other half in the opposite direction. The combined effect is a broadened spectral pattern. And with the right models and enough sensitivity, that broadening can be translated into an estimate of surface rotation speed. For Betelgeuse, One of the key tools in this kind of measurement has been a large radio and millimeter observatory array in the high desert of the southern hemisphere. By observing emission at specific wavelengths where the star's atmosphere is bright, astronomers can map out tiny differences in frequency across the face of the star's projected disk. Regions moving toward us contribute slightly higher frequencies, and regions moving away contribute slightly lower ones. When these maps are assembled, a slow gradient appears, one side subtly shifted in one direction, the other side in the opposite direction. From this gradient, researchers infer a characteristic rotation speed for the outer layers of Betelgeuse, on the order of a few kilometers per second at the surface. For comparison, the surface of our Sun rotates at a few kilometers per second at the equator, even though the Sun is much smaller and less massive than Betelgeuse. If we imagine the Sun swelling to the size of a red supergiant while conserving its rotational properties in a simple way, we would expect its outer layers to turn much more slowly, with speeds closer to a few meters per second rather than a few kilometers per second. This contrast introduces an intriguing tension between simple expectations and what the data suggest. Betelgeuse is huge and massive, yet the measured rotation of its surface appears to remain in the range of several kilometers per second. Under basic conservation of angular momentum, a star that expands dramatically should see its outer layers slow down, just as a spinning skater extends their arms and feels their rotation rate decrease. For Betelgeuse to rotate this quickly at such a large radius, some additional process must either have given it extra spin or prevented it from slowing as much as a straightforward model would predict. There are different ways to respond to that situation. One possibility is that the interpretation of the spectral data needs further refinement. Perhaps because the surface of Betelgeuse is not uniform, large convective cells, bright and dark regions, and complex flows in its extended atmosphere can all influence how the Doppler shifts are distributed. If patterns of rising and sinking gas mimic the signature of rotation in certain ways, they might lead us to overestimate the global spin when we fit the data with simplified models. In that picture, the star's true rotation might still be slower, but we are currently reading a mixture of motions as if it were a simple spin. Another possibility rests not on misinterpretation, but on history. A star like Betelgeuse does not evolve in isolation. If it once had a close companion, orbital interactions could have transferred angular momentum into its outer layers. Over very long times, tidal forces and mass exchange in a binary system can redistribute angular momentum between the orbit and the spins of the stars involved. In some scenarios, the more massive star can draw in gas from its partner, with that inflowing material carrying significant orbital motion. As the gas spirals onto the red supergiant, it can deposit that motion into the outer envelope, leaving the star larger yet still rotating relatively rapidly. In such a history, Betelgeuse would be the visible remnant of a complex interaction. Its present rotation, a record of past exchanges of mass and motion, with a neighbor that may now be faint, merged, or no longer present in the same way. The surface layers we observe would then be shaped not only by internal evolution, but also by these earlier encounters. The idea does not require sudden events. Instead, the transfer of angular momentum can occur gradually, as gas streams flow and mix over extensive stretches of time. Between these two broad families of explanations, measurement influenced by surface structure and genuine spin enhancement through interaction, the data at present do not compel us to choose a single story. They invite us instead to keep both possibilities in view. On one hand, advances in imaging and spectroscopy may reveal more about the cellular patterns on Betelgeuse's surface, allowing us to separate global rotation from local flows. On the other hand, improved understanding of massive star evolution in binary systems may clarify how often such stars experience long episodes of mass transfer that reshape their rotation. In either case, Betelgeuse serves as a calm example of how a specific star can connect observational technique, physical expectation, and the complexities of real astrophysical history. Its apparent surface speed challenges simple scaling from the Sun, yet it does so in a way that points us toward more detailed models, rather than toward contradiction. As instruments continue to refine their measurements and as simulations of stellar envelopes grow more realistic, the story of Betelgeuse's rotation will likely acquire additional layers, with surface dynamics, internal fields, and past companions all contributing to the final picture. For now, we can hold Betelgeuse in our thoughts as one more waypoint in the landscape of stellar extremes. It is not a compact object like a neutron star or a gravastar, yet it brushes against similar themes. How matter moves, how angular momentum is shared, and how observations from far away translate into stories about the internal and external motions of stars. From this bright red point near Orion, our attention can move onward to other cases where rotation, structure, and history intertwine, continuing the broader exploration of how stars across the universe carry their pasts within their present patterns of light and motion. From a distance that turns vast structures into faint points of light, Betelgeuse offers only a limited outline of itself. What appears steady to the eye hides an outer layer in constant motion, shaped not by smooth rotation alone but by large-scale flows that rise and fall across the star's extended surface. To picture this surface, it helps to set aside the idea of a calm, uniform sphere and replace it with something more irregular, where motion is the rule rather than the exception. Models of red supergiant stars suggest that Betelgeuse's outer layers are dominated by enormous convective cells. These are regions where hot material rises from deeper layers, cools as it expands, and then sinks back down again. Each cell can span distances comparable to the orbit of a planet, stretching tens or even hundreds of millions of kilometers across. Within these cells, gas can move at speeds that exceed the rotation rates inferred from Doppler measurements, flowing upward and downward, as well as sideways along the surface. Seen in this way, the star's visible face resembles a vast, uneven pattern of motion rather than a smooth shell turning at a single speed. Bright regions mark where hot material reaches the surface, while darker regions indicate cooler gas sinking back inward. At any given moment, some of these regions move slightly toward us, others slightly away, not because the entire star is rotating rapidly, but because local flows carry material in different directions. From far away, all of these motions overlap in the light that reaches our instruments. This complexity matters because the Doppler method used to infer rotation does not, by itself, distinguish between different kinds of motion along the line of sight. Whether light is shifted because a surface patch is carried around by rotation or because it is lifted upward by convection, the wavelength change looks similar at first glance. When we observe a distant star with limited resolution, these individual patches blur together, and the combined signal must be interpreted through models that assume certain patterns are present. Numerical simulations help clarify how this blurring can influence what we think we see. When three-dimensional models of a red supergiant surface are created, complete with rising plumes and sinking regions, the resulting synthetic images show a mottled pattern of red and blue shifted areas. If these images are examined at full resolution, the irregular structure is clear, with no simple axis of symmetry. But when the same images are blurred to match the resolving power of current instruments, much of that detail disappears. What remains after this blurring is often a smooth-looking gradient across the stellar disk, with one side appearing slightly more red-shifted and the other more blue-shifted. In simulations, this effect occurs in a large fraction of cases, even when the star is not rotating particularly fast. The apparent gradient emerges from the averaging of many smaller motions rather than from a single, coherent spin. In other words, the observational signature of rotation can arise even when rotation is not the dominant motion at the surface. This insight provides a straightforward way to reinterpret the measurements that suggested a rapid surface rotation for Betelgeuse. If large convective flows dominate the outer layers, and if the resolution of our observations blends these flows together, then the inferred rotation speed could reflect an average pattern rather than a true global turn. In this view, the star may still rotate, but more slowly than the initial numbers imply, with convection supplying most of the Doppler signal. Independent observations of Betelgeuse's variability support the idea of a highly dynamic surface. A few years ago, the star's brightness decreased noticeably over a span of months, drawing attention from both professional astronomers and casual skywatchers. Follow-up studies indicated that this dimming was linked to a large-scale ejection of material from the star's surface. Hot plasma rose outward, cooled, and condensed into dust, temporarily obscuring part of the star and reducing the light that reached Earth. Such an event highlights the scale and vigor of the processes at work in the outer layers of a red supergiant. Rather than changing gradually and uniformly, the surface can undergo significant rearrangements over relatively short astronomical intervals. These rearrangements alter not only the star's brightness, but also the distribution of motion across its face, affecting the spectral signatures used to infer rotation and other properties. When this kind of variability is taken into account, the picture of Betelgeuse becomes less about a single surprising number and more about a system whose behavior depends on when and how it is observed. A Doppler measurement taken during one phase of surface activity may emphasize certain flows, while a measurement taken later may highlight different patterns. Without a long sequence of observations covering many cycles of surface motion, it is difficult to separate persistent rotation from transient convective effects. For this reason, current assessments of Betelgeuse's rotation remain provisional. A single snapshot, however precise, cannot fully capture the evolving balance between global spin and local motion. What is needed is a series of measurements taken over extended periods with improved resolution and sensitivity, allowing astronomers to track how Doppler patterns change as surface features rise, fade, and reappear. By comparing these changes across time, it becomes possible to identify which components remain stable and which vary, gradually teasing apart rotation from convection. Until such data are available, Betelgeuse occupies an intermediate position in our understanding. It may indeed rotate faster than simple models predict, perhaps due to interactions earlier in its history. Or it may rotate more modestly, with its apparent speed amplified by the restless behavior of its surface. Both possibilities fit within what we currently know, and neither requires us to force the observations into a single narrative. In this state of open interpretation, Betelgeuse serves as a reminder that stars are not static objects defined by a few fixed parameters. They are evolving systems, shaped by internal flows, past interactions, and the limits of how we observe them from afar. The challenge lies not in choosing a dramatic explanation, but in allowing the data to accumulate slowly, refining our models as new details come into view. As we step back from this particular star, the broader theme returns. The universe often presents structures whose outward appearance masks complex internal motion. Whether we look at compact remnants near the edge of black hole formation or at swollen giants like Betelgeuse, the balance between what we infer and what we directly observe remains delicate. For now, Betelgeuse continues to turn, convect, and shed material under its own gravity, offering a living example of how uncertainty and understanding coexist in the study of stellar extremes. High above the plane of the Milky Way, in a modest arc of stars known as the Northern Crown, there exists a system whose behavior unfolds in long, patient intervals. T Coronae Borealis, sometimes called the Blaze Star, is not a single star but a pair bound together by gravity, orbiting a common center from a distance of roughly a few thousand light-years from Earth. Most of the time, this system remains faint, well beyond the reach of the unaided eye, blending quietly into the background of the constellation. Within the system, the two stars are very different in character. One is a red giant, an aging star that has expanded far beyond its earlier size, its outer layers extended and loosely held. The other is a white dwarf, the compact remnant of a star that has already passed through its own long evolutionary arc. Dense, small, and supported by electron degeneracy pressure rather than ongoing fusion, the white dwarf carries a strong gravitational pull despite its modest physical size. Their orbital dance is slow and steady, and it is this pairing that sets the stage for the repeating displays that have drawn attention to the system across generations. As the red giant expands, its outer atmosphere drifts closer to the region where the white dwarf's gravity becomes dominant. Gas from the red giant does not fall straight across the gap, but forms a stream, guided by gravity and orbital motion, gradually settling onto the surface of the white dwarf. This transfer is not dramatic in the moment. It unfolds gradually, over years and decades, with hydrogen-rich material accumulating as a thin layer atop the dense stellar remnant. On the white dwarf's surface, gravity compresses this incoming gas to extreme densities. Unlike a normal star, the white dwarf does not regulate its surface through steady fusion. The material simply piles up, becoming hotter and more compressed as more gas arrives. Pressure builds. Not because the star is changing internally, but because the added layer is being forced into a smaller and smaller volume by gravity alone. In this way, the white dwarf acts as a reservoir, quietly storing fuel rather than consuming it continuously. Eventually, the accumulated hydrogen reaches conditions where nuclear reactions can begin. When that threshold is crossed, fusion ignites rapidly across the surface layer. The result is a nova, a sudden release of energy that ejects the accumulated shell outward into space. The underlying white dwarf remains intact, its dense core unchanged, while the surface layer is swept away. From Earth, this event appears as a sharp increase in brightness, transforming a faint, barely detectable system into a visible star for a brief period. The increase in light can be dramatic. Over the course of days or weeks, the system may brighten by more than 1,000 times, reaching a level comparable to some of the more familiar stars in the night sky. After the outburst, the ejected material expands and cools, the fusion subsides, and the system gradually returns to its earlier faint state. What remains is the same binary configuration as before, ready to begin the cycle again. This process distinguishes a nova from other stellar explosions. In a supernova, the star itself is fundamentally altered or destroyed, marking a single, final transformation. In a nova, only the surface layer is involved. The white dwarf survives, continuing its quiet existence, and the red giant continues to supply material over time. The balance between gravity and pressure remains intact on the larger scale, allowing the system to repeat its behavior rather than bringing it to an end. Historical records show that T Coronae Borealis has followed this pattern more than once. In the 19th century, observers noted a new star appearing in the northern crown, bright enough to be seen without instruments. Decades later, a similar event was recorded, matching the same position in the sky. These observations, separated by many years, revealed that the outbursts were not isolated accidents, but part of a repeating cycle, with intervals measured in many decades rather than days or months. Because the timing of each nova depends on how quickly material accumulates and how conditions develop on the white dwarf's surface, predictions can only be approximate. Astronomers can estimate when enough gas is likely to build up again, but the exact moment of ignition remains uncertain. The system does not follow a precise clock, yet its long-term rhythm is clear enough that future outbursts can be anticipated within a range of years. For those studying stellar extremes, the blaze star offers a different perspective from compact objects like neutron stars or black hole candidates. Here, gravity does not overwhelm all opposing forces, nor does pressure create a permanent new structure. Instead, the system cycles between quiet accumulation and brief release, governed by the interaction between two stars at very different stages of evolution. The white dwarf's role is defined by electron degeneracy pressure, while the red giant's extended atmosphere provides the material that makes the cycle possible. This repeating nova behavior also highlights how stellar systems can remain stable while producing striking changes in appearance. The underlying structure persists, even as the visible brightness varies dramatically. From a distance of thousands of light years, these changes appear sudden, yet they arise from processes that unfold patiently over long spans of time. As we move onward in our exploration of stellar extremes, systems like T Coronae Borealis remind us that not all remarkable cosmic events are singular or final. Some are part of ongoing patterns, shaped by balance rather than collapse, and by interaction rather than isolation. In these long cycles of build-up and release, the universe continues its quiet work, offering moments of brightness without demanding an ending, and allowing observation to remain open rather than complete. When we speak about how bright a star looks in the sky, we are not describing its true power, but how much of its light reaches our eyes from Earth. Astronomers use a scale called apparent magnitude to make these comparisons, a scale that runs in a direction that can feel counterintuitive at first. On this scale, smaller numbers mean brighter objects, and larger numbers mean fainter ones. The sun, overwhelming in daylight, sits far into negative values, while the faintest stars visible to the unaided eye rest near the upper limit of what human vision can detect on a dark night. Most of the time, the blazed star lies well beyond that limit. With an apparent magnitude around 10, it remains invisible without a telescope, quietly present but unnoticed. During a nova outburst, however, its position on the scale shifts dramatically. The system brightens until it reaches values around 2 or 3, placing it among the brighter stars of the night sky. At that level, it becomes comparable to Polaris, the North Star, which many people already recognize as a steady reference point. The effect is that a star which was previously absent from casual view suddenly takes its place among the familiar points of light. For an observer under a dark sky, this change can feel abrupt. One night, the region appears unremarkable, filled only with faint stars arranged in subtle patterns. Then, within a short span of time, a new point becomes visible, shining clearly where none was noticed before. The brightness does not rival the most brilliant stars in the sky, yet it stands out enough to draw attention, especially to those who know the usual appearance of that part of the heavens. This level of brightness helps place the blazed star in context with other stellar events. A nova increases a star's apparent brightness by thousands of times, which is impressive on its own scale. A supernova, by contrast, can outshine an entire galaxy for a brief period, brightening by factors millions of times greater than its original state. Some historical supernovae were bright enough to be seen during the day, casting faint shadows and remaining visible even in sunlight. The blazed star's outbursts do not reach that level. They belong firmly to the realm of the night sky, noticeable and memorable, but not overwhelming. Thinking in these terms helps set expectations. If a supernova is an event that dominates the sky, the blazed star is something more modest, a brief addition to the familiar pattern of stars that rewards patience rather than startling the senses. Its appearance fits naturally into the nighttime environment, asking only for darkness and a moment of attention. Locating the blazed star begins with a few well-known guides. One useful starting point is Arcturus, a bright orange star that stands out in the constellation Boötes. From there, the eye can trace a gentle path toward Vega, one of the brightest stars in the northern sky. Between these two landmarks lies a small, curved arrangement of stars known as Corona Borealis, the northern crown. It appears as a delicate arc, easy to overlook unless one knows to search for it. Within this arc, the blazed star sits near one end of the curve, close to the boundary with the neighboring constellation Hercules. Under ordinary circumstances, nothing about this spot draws attention. During a nova outburst, however, a new point of light appears near the arc, subtly reshaping the crown's outline. The arc gains an extra jewel, one that was not present before, and that change becomes the key sign that the system has entered another active phase. This way of finding the star relies more on pattern recognition than on precise measurement. The constellations serve as a map, not because their shapes have physical meaning, but because they help us organize the sky into familiar regions. When a new light appears within one of those regions, its novelty stands out against the remembered pattern. Over successive nights, the light slowly fades, and the crown returns to its quieter form. What makes this process distinctive is its accessibility. No advanced equipment is required, and no special technique is needed beyond knowing where to look. The experience bridges scientific understanding and direct observation, showing how a process governed by gravity, pressure, and nuclear reactions can become visible to the human eye across thousands of light years. In the broader story of stellar extremes, the blazed star offers a gentle contrast. It is neither the steady brilliance of a main sequence star nor the final collapse of a supernova. Instead, it occupies a middle ground, where balance is disrupted and restored repeatedly, and where change arrives in cycles rather than in a single, irreversible moment. As attention drifts from the mechanics of nova explosions back toward the wider universe, this example lingers as a reminder that some of the most interesting cosmic events are those that return. They allow us to notice, to compare, and to wait again, holding space for the next appearance without needing to define an ending. In that sense, the blaze star fits naturally into the quiet rhythm of the night sky, offering brightness without finality and observation without closure. Long before individual stars and galaxies took on their familiar shapes, the universe itself began to change in a way that still leaves a measurable imprint. One of the quiet facts we carry with us is that space is not static. Distances between faraway galaxies increase over time. Not because the galaxies are moving through space like sparks from an explosion, but because space itself is stretching. This steady widening provides one of the simplest clues we have about the universe's age. The idea can be framed in terms of a present-day expansion rate, often summarized by what is called the Hubble constant. In everyday language, it tells us how much faster distant galaxies appear to recede as their separation increases. If two galaxies are twice as far apart, the space between them expands roughly twice as fast. Expressed intuitively, the expansion adds something like tens of kilometers per second for every few million light-years of distance. This rate is small on local scales, yet, over cosmic distances, it becomes the dominant pattern. Once we accept that expansion is real and measurable, a natural step follows. If distances are increasing now, they must have been smaller in the past. By tracing the expansion backward in time, like rewinding a very slow film, we can estimate how long it would take for all those separations to shrink toward a much denser state. This backward extrapolation does not describe a single point in space, but a moment when the entire observable universe was hotter, denser, and more closely packed than it is today. From this reasoning alone, we arrive at a timescale measured in billions of years. To make this estimate meaningful, a few broad assumptions are needed. On the largest scales, the universe appears similar in every direction and at every location. Galaxies cluster into groups and filaments, leaving large voids in between. Yet when we average over immense volumes, these irregularities smooth out. In this averaged view, no place is special, and no direction stands out. The laws of physics we measure locally are assumed to apply everywhere, allowing a single set of equations to describe the whole. Under these assumptions, the expansion history can be connected to the contents of the universe. Different components influence how the expansion changes over time. Ordinary matter, the kind that makes up stars, planets, and gas, pulls inward through gravity. Dark matter, unseen but detectable through its gravitational effects, contributes additional pull. Dark energy, inferred from the observed acceleration of expansion, acts in the opposite sense on the largest scales, encouraging space to stretch faster over time. The balance among these components shapes the universe's past and future behavior. One of the most informative records of this balance comes from the cosmic microwave background, often shortened to CMB. This faint radiation fills all of space and arrives at Earth from every direction with nearly the same temperature. It is the remnant light from a time when the universe was only a few 100,000 years old, long before stars existed. At that stage, matter and radiation had just decoupled, allowing light to travel freely for the first time. What we see today is that ancient light, cooled and stretched by billions of years of expansion. Although the CMB appears remarkably uniform, it carries tiny variations in brightness and temperature. These small differences reflect slight variations in density in the early universe, the seeds from which galaxies and larger structures eventually grew. By measuring the pattern of these variations with high precision, missions such as Planck have provided a detailed snapshot of the universe at that early time. From this snapshot, scientists infer not only the relative amounts of different cosmic components, but also the overall expansion history. The results point to a universe composed mostly of ingredients that do not emit light. Roughly a small fraction consists of ordinary matter, with a larger share made up of dark matter, and the largest contribution coming from dark energy. When these proportions are fed into the equations that describe an expanding, homogeneous universe, the model that emerges fits a wide range of observations at once. The expansion rate measured today, the pattern of the CMB, and the brightness of distant supernovae all align within this framework. From that alignment comes an estimated age of around 13 to 14 billion years, with uncertainties narrowed to only a small percentage. What is notable here is that this age does not depend on knowing the detailed nature of dark matter or dark energy. Their precise identities remain open topics, yet their effects on cosmic expansion and structure formation are well constrained by observation. Much like measuring the motion of a vehicle without knowing the details of its engine, we can track how these components influence the universe's growth without fully understanding what they are made of. Their gravitational and dynamical roles are enough to anchor the timeline. This approach highlights a broader theme in cosmology. Often, progress comes from identifying consistent patterns in how things behave, even when their underlying essence is still unclear. Dark matter shapes the way galaxies rotate and cluster. Dark energy governs the large-scale expansion. By focusing on these roles, models can remain predictive and coherent, allowing time, distance, and structure to be linked in a single narrative. Of course, this narrative remains open to refinement. If new observations reveal that one of the foundational assumptions is incomplete, or if measurements of expansion at different epochs continue to show subtle discrepancies, the inferred age may be adjusted. Such revisions would not erase the method, but would update the inputs and the balance among components. The number itself is less important than the web of observations that supports it. Within the context of stellar extremes, this cosmic timescale provides a quiet backdrop. White dwarfs, neutron stars, and even hypothetical exotic stars all exist within a universe whose age sets the maximum duration for their histories. When individual objects appear to challenge that duration, as with some unusually old stars, the tension invites careful re-examination rather than immediate contradiction. It may point to refinements in stellar models, measurement techniques, or cosmological parameters, all working together to sharpen the picture. As we move through these ideas, the age of the universe emerges not as a single, isolated fact, but as a convergence of expansion, background light, and unseen components acting over immense scales. It is a number that summarizes many layers of observation without closing off further inquiry. In that sense, it mirrors the broader theme of this journey: balance without finality, understanding that remains flexible, and a cosmos whose story continues to unfold even as we trace its earliest chapters. Not all witnesses to the early universe are distant or faint beyond reach. Some reside surprisingly close, carrying within their light a record of conditions that prevailed when the cosmos was young. One such star is HD 140283, often called Methuselah, a solitary object located only a few hundred light-years from Earth. In astronomical terms, this is nearby, close enough that its distance can be measured with unusual precision. That proximity turns Methuselah into a valuable reference point, allowing astronomers to examine an ancient stellar life with tools that are rarely available for stars of comparable age. What sets Methuselah apart is not its brightness or size, but its composition. It contains remarkably small amounts of heavy elements, the atoms forged inside earlier generations of stars and spread through space by stellar winds and explosions. In Methuselah, those elements are scarce, suggesting that it formed before the universe had been significantly enriched. Its atmosphere preserves a chemical simplicity that points back toward a time when stars were just beginning to appear, emerging from gas that had undergone little prior processing. Because Methuselah lies so close, its distance can be determined through parallax measurements with exceptional care. Instruments aboard the Hubble Space Telescope refined this measurement, reducing uncertainty in its intrinsic brightness. Once that brightness is known, stellar models can be applied to estimate how long such a star would take to reach its present state. In this way, Methuselah becomes more than a curiosity. It becomes a clock, one that can be read independently of the cosmic microwave background or the overall expansion of space. When that clock was first read in detail, the result drew attention. An analysis published in the early part of the last decade suggested that Methuselah's age was around 14.5 billion years, with an uncertainty of less than a billion years. Taken at face value, the central estimate exceeded the widely accepted age of the universe, which stands near 13.5 billion years. Within the margins of error, the star's age could still be consistent with cosmic history, yet the numbers sat uncomfortably close to the edge. This situation created a quiet tension rather than a dramatic contradiction. No one suggested that the star truly formed before the universe itself, but the overlap between the star's estimated age and the cosmic timeline highlighted how closely different measurements now approach one another. The apparent mismatch served as a reminder that when uncertainties shrink, even small discrepancies can become meaningful. Here was a case where stellar physics and cosmology met directly, each testing the limits of the other. The response was not to discard the cosmological model, nor to dismiss the stellar data, but to look more closely at both. Stellar age estimates depend on detailed models of how stars evolve over time, including how energy moves through their interiors and how composition affects luminosity and temperature. Small adjustments in these ingredients can shift the inferred age by hundreds of millions of years. For a star as old as Methuselah, those shifts matter. Over the following years, additional observations and refined modeling helped clarify the picture. Measurements of the star's oscillations, subtle rhythmic changes in brightness linked to internal structure, provided new constraints on its mass and internal composition. Interferometric techniques improved estimates of its size, and updated analyses of its chemical makeup sharpened the input parameters used in evolutionary models. Each refinement nudged the star's age slightly downward. As these updates accumulated, Methuselah's estimated age settled into a narrower range. Many results placed it between 12 and 14 billion years, with a growing preference toward values close to 13 or 13.5 billion. Within this range, the star's age aligns comfortably with the age of the universe once uncertainties on both sides are considered. The earlier tension eased, not through a single decisive correction, but through a gradual convergence of independent measurements. This process illustrates how scientific understanding often advances. An apparent inconsistency draws attention, prompting closer scrutiny. Models are revisited, assumptions examined, and data refined. The outcome is not a reversal, but a better alignment between different lines of evidence. In Methuselah's case, the universe did not need to become older, nor did the star need to become young. Instead, improved clarity brought both into a shared frame where they could coexist without strain. Even without exceeding the universe's age, Methuselah remains exceptional. It stands among the oldest known stars, a survivor from an era close to the beginning of stellar formation. Its existence places a lower bound on how soon after the early expansion stars could condense from primordial gas. That bound serves as an independent check on cosmological timelines, complementing information drawn from background radiation and distant supernovae. In this role, Methuselah functions like an ancient landmark. On Earth, the oldest rocks do not tell us everything about planetary history, yet they confirm that certain events must have occurred by a given time. Similarly, stars like Methuselah confirm that the universe had already cooled and structured itself enough to form long-lived stars relatively early in its history. They anchor abstract models in tangible objects that can be observed and measured directly. As attention moves beyond this particular star, the broader lesson remains. The age of the universe is not established by a single method or observation, but by the convergence of many. Expansion rates, background light, stellar lifetimes, and chemical evolution all contribute pieces to the same story. When one piece seems out of place, it invites refinement rather than alarm. Methuselah's quiet presence nearby reminds us that uncertainty and precision often travel together. The closer we come to the limits of measurement, the more carefully different fields must be woven into a consistent whole. In that careful weaving, ancient stars do not undermine our understanding of cosmic time. Instead, they help shape it, offering steady points of reference as our picture of the universe continues to mature and expand. Long before a star settles into a steady balance like the sun, its story begins in regions that appear dark and quiet from a distance. These are molecular clouds, vast collections of cold gas and dust drifting through the spiral arms of galaxies. Within them, gravity works patiently, drawing material together into denser pockets. From these pockets, protostars emerge, still hidden from direct view, their light softened and filtered by the clouds that surround them. In places such as the Orion Nebula, this early stage can be observed indirectly. There, astronomers find Herbig-Haro objects, luminous knots and streaks that mark where fast-moving jets of gas collide with the colder material around them. One example, known as HH34, reveals a young star in the midst of formation. The star itself remains buried inside its natal cloud, but along its rotational axis it sends out narrow streams of hot gas. These streams travel at speeds far higher than the gentle motions typical of mature stars, cutting through the surrounding medium until they slow and glow at their points of impact. Seen in images, these jets form elongated structures with subtle colors that trace shock fronts rather than surfaces. They appear briefly on astronomical timescales, lasting only a few thousand years before fading or changing shape. In the life of a star, which spans millions or billions of years, this phase is fleeting. Yet, it is precisely this brevity that makes such observations valuable. They allow us to witness star formation not as a theoretical sequence, but as an active process unfolding in real environments. The jets themselves arise from a balance between gravity and motion. As material falls inward toward the forming star, it carries angular momentum, flattening into a rotating disk. From this disk, magnetic fields help channel some of the infalling matter outward along the poles. The result is a pair of opposing jets, carrying excess angular momentum away and allowing the central object to continue growing. In this way, the early star manages its own formation, regulating how material settles and how energy is released. Beyond Orion, similar scenes play out in quieter regions, such as the Taurus molecular cloud. There, systems like XZ Tauri show how dynamic these early environments can be. XZ Tauri consists of two young stars orbiting each other at a distance comparable to the scale of our own outer solar system. Surrounding them is a bubble of gas that has been observed expanding over time. Images taken years apart reveal that this bubble grows measurably, offering a rare chance to see motion across the sky rather than infer it indirectly. This expanding structure reflects repeated outflows from the young stars, interacting with earlier material that was ejected during previous episodes. Instead of a single explosive event, the scene records a history of intermittent activity, layered one upon another. The surrounding cloud becomes a kind of archive, holding the imprint of each phase of accretion and release. Nearby, HL Tauri presents a different but related view of stellar infancy. At its center lies a young star surrounded by a broad disk of dust and gas. High-resolution observations show that this disk is not smooth. Instead, it contains gaps and rings, subtle clearings that suggest material is already beginning to organize itself into larger bodies. These are the earliest outlines of planets, forming while the central star itself is still in the process of assembly. In another system, V1213 Tauri, the disk is oriented almost edge-on from our perspective. The central star is largely hidden, its light blocked by the dense plane of dust. What stands out instead are two narrow jets emerging above and below the disk, forming a symmetric pair. These jets illuminate the surrounding cloud, producing a classic Herbig-Haro structure known as HH30. The geometry makes the relationship between disk and jets especially clear, showing how material flows inward along one plane and outward along another. Together, these examples reveal a consistent pattern. At the earlier stages, stars are rarely isolated points of light. They are systems, defined by disks, jets, and interactions with their surroundings. Gravity draws material inward, while pressure, rotation, and magnetic effects shape how that material is redistributed. Even before nuclear fusion becomes the dominant source of energy, the balance between inward pull and outward response is already present, guiding the star's development. Another object in the Orion region, HH24, emphasizes how deeply embedded some protostars remain. In this case, the central source is almost completely obscured by dense clouds. What we see instead are two thin, luminous jets extending in opposite directions, piercing the darkness like narrow beams. Each jet ends in a brighter knot where it meets resistance, marking the boundary between fast-moving gas and the surrounding medium. The star itself remains implied rather than seen, its presence revealed only through these outward signs. These observations underscore how much of star formation happens behind veils. Direct light from the forming star is often hidden, but the interaction between its outflows and the environment leaves visible traces. By studying these traces, astronomers infer the properties of objects that cannot yet be observed directly. The shape, speed, and orientation of jets provide clues to the mass, rotation, and evolutionary stage of the protostar that produces them. What unites all these scenes is their transitory nature. Herbig-Haro objects fade as jets weaken or change direction. Disks evolve as material settles into planets or is dispersed by radiation and winds. The chaotic motions of early accretion gradually give way to the more stable patterns of mature stars. Over time, the violent exchanges of gas quiet down, and the star enters a long period where fusion balances gravity in a relatively steady state. Seen in the context of stellar extremes, these early phases provide a counterpoint to later stages marked by collapse or explosion. At birth, stars are defined by growth rather than loss, by assembly rather than breakdown. Yet the same principles apply throughout. Gravity remains the inward pull. Pressure and motion provide balance, and structure emerges from the interplay between them. As attention moves forward along the stellar timeline, from formation to maturity and eventually to remnant states, these images of protostars linger as reminders of where the journey begins. Before white dwarfs, neutron stars, or hypothetical exotic objects come into view, there is this quieter beginning, written in jets of light and expanding bubbles within dark clouds. In these regions, the universe continues its slow work, turning diffuse material into concentrated sources of light, without haste and without finality, leaving each stage open to the next. Near the later stages of stellar evolution, some stars begin to leave visible traces that are less about brightness and more about form. These traces appear not as points of light, but as extended structures shaped by motion, timing, and companionship. In this phase, gravity still draws matter inward, yet pressure, radiation, and orbital motion redirect that material outward, allowing geometry itself to become part of the story. One of the clearest examples is LL Pegasi, a system whose surrounding gas and dust form a near-perfect spiral. At its center sits a star in the process of shedding its outer layers, paired with a companion in a slow orbital dance. As the larger star releases material, that material does not flow outward evenly. Instead, it carries the imprint of the binary orbit, winding into a pattern that resembles a carefully drawn spiral. Each loop corresponds to a full orbit of the system, taking many centuries to complete. While the outflowing gas moves outward at speeds measured in tens of thousands of kilometers per hour. The star itself is largely hidden behind dust. Yet the spiral remains visible because light scatters off the expelled material. What we see is not the star's surface, but the history of its motion written into space. The structure is orderly, repeating, and remarkably stable, showing how predictable dynamics in a binary system can shape matter far beyond the star itself. In this case, geometry becomes a record of time, marking cycles that are far longer than any human observation window. Other systems display less regularity. HD 44179, often associated with the Red Rectangle Nebula, presents a form that appears almost angular, closer to a box or an X-shaped figure than to a smooth shell. Light from the central region reflects off dust arranged in sharply defined planes, creating intersecting beams against a dark background. Unlike the spiral of LL Pegasi, this shape does not immediately reveal its formation process. The presence of a binary system is again suspected, yet the precise arrangement of flows and reflections remains an active area of study. Three-dimensional models and observations across multiple wavelengths suggest that winds, disks, and orbital motion all contribute, but no single mechanism explains every detail. This uncertainty does not weaken the picture. It highlights how diverse the outcomes of late stellar evolution can be, even when stars begin from similar physical conditions. Some stars near the end of their lives express change not through shape alone, but through rhythm. Rs Puppis is a Cepheid variable, a star whose brightness rises and falls in a regular cycle lasting several weeks. The star expands and contracts slightly, driven by a balance between gravity and internal pressure, producing predictable variations in light. What makes Rs Puppis distinctive is its surrounding cloud of dust, which turns these variations into a spatial pattern. As the star brightens, light travels outward and reflects off dust at increasing distances. Because light takes time to cross space, the reflected illumination appears as expanding rings, a phenomenon known as a light echo. Each pulse becomes a moving wave of brightness, revealing the three-dimensional structure of the surrounding material. Through this effect, changes in a single star allow astronomers to map space around it, using time itself as a measuring tool. In a different regime of stellar extremes, AG Carina stands out for its luminosity and mass loss. It is among the most luminous stars in the Milky Way, radiating energy at a rate that drives powerful stellar winds. These winds carry material away from the star at speeds of several million kilometers per hour, sculpting shells and filaments in the surrounding gas. The star's brilliance is not steady. It varies over time as internal conditions shift, redistributing energy between radiation and expansion. Images of AG Carina show a small, intense, central source embedded within a complex nebula of its own making. The surrounding structures reflect episodes of mass loss rather than a single event, suggesting a life marked by repeated adjustments rather than a simple linear path. Such stars live comparatively brief lives on cosmic timescales, not because they are unstable, but because their high luminosity accelerates the processes that govern their evolution. At the most compact end of stellar remnants, the narrative changes again. In some galaxies, pairs of neutron stars orbit one another for millions of years, gradually losing energy through gravitational radiation. In 2017, such a system in the galaxy NGC 4993 produced a signal detected by gravitational wave observatories on Earth. The waves marked the final moments of the inspiral, carrying information about masses and motion across a distance of more than 100 million light-years. Shortly after the gravitational signal arrived, telescopes observed a transient source of light at the same location. This kilonova emitted radiation across many wavelengths, from high-energy gamma rays to infrared light. The event released material enriched with heavy elements, formed under conditions that exist only when neutron-dense matter is rapidly reconfigured. The observation linked stellar evolution, gravitational waves, and cosmic chemistry into a single sequence, showing how compact remnants contribute to the composition of the universe. Across these examples, a common theme emerges. As stars approach the later stages of their existence, balance does not vanish. It changes form. Pressure may give way to radiation-driven winds, orbital motion may shape outflows, and gravity may guide matter into new configurations. The results are not uniform endings, but a wide range of structures and signals, each reflecting a different pathway through stellar life. These shapes, rhythms, and events do not announce a final statement about stars. Instead, they offer glimpses into processes that unfold gradually, sometimes cyclically, sometimes briefly, always within the same physical principles that govern more familiar stars like the Sunday. By observing them, we do not close a chapter, but widen the frame, allowing late-stage stars to take their place within the broader, ongoing pattern of the universe. Looking back over the path we have traveled, a single thread becomes visible, running through every story we have encountered. From ordinary stars like the Sun to white dwarfs, neutron stars, black hole candidates, and even hypothetical structures such as gravastars, all of them revolve around one enduring question: how does gravity find balance, or fail to find it, under different conditions of matter and space-time? There is no sharp conclusion here, only thresholds and transition regions where our understanding remains open. Seen through this lens, the universe is not a finished narrative. It is more like an extended piece of music, shaped by resonant passages and long, quiet pauses. It is within those pauses that reflection becomes possible, where questions can rest without urgency, and where we can accept that not everything needs to be fully explained all at once. Thank you for taking the time to listen and for accompanying this journey to its closing moments. In the times ahead, we will continue moving gently into new surprises and unnamed mysteries of the vast cosmos, where each discovery opens yet another quiet space for contemplation.